So I'm actually live now. Yeah, okay, yeah. No, no. No, it was my fault. I didn't turn it on. Okay, no Giuseppe. So I guess where we left off last lecture was in the middle of a discussion of how to understand the corrections that come from the high energy portion of the Hilbert space to the truncated conformal spectrum approach, and ultimately how to develop an RG scheme for the truncated conformal spectrum approach. So, you know, we had our Hamiltonian. Which we had written in block form in terms of the high and low energy portions of the Hilbert space. And in terms of our spectrum, we'd managed to get up to a certain point in the energy spectrum. So this was the low energy portion of the Hilbert space. The high energy portion of the Hilbert space, and we'd gotten up to here either just using TCSA or TCSA plus some Wilsonian numerical renormalization group. And by what I mean, when we say we've gotten up to this portion of the Hilbert space, we'd expressed okay, stop that. We'd expressed the eigenstates we'd expressed our eigenstates of the full Hamiltonian in terms of the basis of H known involving states of H known, eigenstates of H known up to this cutoff energy. And where we left it off was I'd given you an expression for the correction to the energy coming from the high energy portion of the Hilbert space in terms of a conformal two-point function. Which let me but in terms of this conformal two-point function, it was a funny two-point function. it was funny in the sense that if we really what we mean by really what we mean by this two-point function is that we insert a resolution in the identity, a restricted resolution in the identity between the two fields, I'm not going to want to try it like that. So really what we mean by this restricted two-point function is that we insert a resolution in the identity, partial resolution in the identity between the two fields only involving states above the cutoff energy. And so the question is, how do we evaluate this? And actually, it's rather nice. Conformal field theory gives us the ability to compute this type of object. And the way one does it is you note that this matrix element here really can be using time translational invariance, can be written you can extract the temporal dependence of it, and you see that it has this e to the minus ek tau. And so the way you evaluate this correlation function is to evaluate its unrestricted counterpart. Evaluate its unrestricted counterpart. You then Taylor series, do a Taylor series expansion in e to the tau, and only keep terms in the Taylor series involving powers of e to the tau greater than ek. So let's do that. So the easiest way to do this is the easiest way to evaluate this unrestricted correlation function is not to do so relative to two particular states in an M, but to do it more generally. And to do it more generally, we can use an OPE. And, well, let's see, how do we want to do this? If we remember, it's important to remember that these perturbing fields, when I write phi perturbation tau, what I really mean is the integral over the field over the system size. But then you can just proceed. And so if we do an OPE on this, on these two fields, well, here, let's do it this way. An OPE basically involves replacing these products of fields by a sum over some individual fields or effectively what it does is it extracts the most singular part of the products of these two fields. So when I write this, there's really, I have to understand that there's less singular terms here. But these less singular terms, if you actually go ahead and try to take them into account, you see that what happens is that they're in the contribution to this energy correction is down by some power of the cutoff. So these less singular terms are less important. I can't say definitively that they're not important at all, but and I'll explain that further, but at least they, if you look in terms of how they depend on the cutoff, there's at least they're suppressed by some power of the cutoff. This is this constant C phi pp is the structure constant that Slava was talking about yesterday in the context of d-dimensional conformal field theories, but it's the same object. So it's really, you know, if you this would appear if you took, it's really let's use his notation. It's the constant that appears in this 3-point function that was discussed yesterday. And for a general conformal field theory, of course, these things aren't necessarily known, but at least for the quantumizing model, which has been the subject of the sort of the test bed for most for my lectures, these constants are well known. Okay. So you do an OPE, the space-time dependence gets expressed in this function, which so this space-time function is just given by this, where, well, here, let's be clear what we have here. We have Z is just the exponential of minus 2 pi r at t plus ix. Delta p is just the scaling dimension of the perturbing field. So for Ising, for the Ising perturbation, the perturbing field is the spin operator. And so delta sigma is 1/8. Delta phi is the scaling dimension of the fields that appear in the OPE of the perturbing fields. And for Ising, the fields that appear in the OPE of the spin field and the spin field with itself is basically the identity field plus the operator that corresponds to the energy density. So that would be basically the fermion. Yes. And the structure constant of the sigma field with the sigma field and identity is just 1, because typically you use a conformal normalization that when you have the identity in the structure constant and the other two fields are the same, you usually use this normalization, or that's the standard normalization of the fields. And the other structure constant you would need would be the sigma field with epsilon, and I think in my conventions it's 1 over the square root of 2. Or yes. Okay. So far this is, when one computes this OPE, what one is doing is one is effectively inserting an unrestricted resolution of the identity between the fields, and the question is now, how do we get back to the restricted sum that we're actually interested in for computing this energy correction? Well, it's actually, once we've written this, once we have the expression for the fields in terms of this f function, all we really have to do, remember, we're interested in isolating powers of e to the minus 2 pi over r tau, because this energy, this really has the form of some, it really has the form of some integer like that, where, so if we just Taylor series expand this, then we can isolate powers in tau of this, and then just toss away the low-lying powers. So So the Taylor series expansion of a quantity like this is just given, it just has this Taylor series expansion, a nice expression in terms of gamma functions. And of course you have to, this is the absolute value, So of course you have to worry about expanding not just in terms of z, but z bar, where z bar of course is just that. So you insert these Taylor series expansions into this expression. You do the R integration, the spatial integrations, and then you end up with something of the form. So let me erase this. So you get an R squared from the spatial integrations. Two delta P. Squared. Okay, grotesque detail. I think that's K. Where this constant decay delta P minus where this constant decay is just the it's just that. Okay. So we've now reduced the energy correction to basically evaluating the expectation value of some one-point function. Once we've done this Taylor series, this k greater than nc, where nc is basically the dimensionless cutoff. We've done the Taylor series expansion and we restricted the sum. And so then we have expressed everything in terms of computable quantities. These matrix elements of the one-point function of the field are precisely the type of information that we need to run the TCSA in the first place. These are sort of the basic ingredients of the TCSA. So we already, if we've gotten this far, we already know how to compute this object. Okay. Now, if your cutoff is high enough, what you can do is you can, in this denominator, you can just ignore this portion of the term, because is going to be at least NC, and if NC is large, this term just goes away. And you can simplify the expression of the energy correction to evaluating the one-point function of the field phi in with regards to the full eigenstate of at least the low energy sector. So this, I mean, now, since we've now reduced the energy correction to this one-point function, what one can do, or what one can, instead of thinking of this as just the energy correction, you can think of it as a counter term to be added to your Hamiltonian. No, let's do it like this. So we have our structure constant. So P delta phi and EC minus 2 delta phi. What the hell is that? So instead of computing this energy correction, if we just added this counter term to the Hamiltonian from the start, we would have the same effect. So we'll... I don't know what that P is. What is that P? Okay. Now, let's just be clear what this is. EC equals, yeah. Where we've written it in terms of dimensionless cutoff energy. Now, one can go to higher orders in this type of argument, and the sort of the scaling of the energy correction at higher orders in perturbation theory takes this form. Now, I've expressed things in terms of this cutoff energy, and you see that for large R, so you see that for large R, you expect the perturbation theory to break down because the cutoff energy becomes small, or this. Yeah, let's just say perturbations. And you can actually see, I mean, this is if you remember, this is the numerical data coming from the application of the truncated conformal spectrum approach for the truncated conformal spectrum approach plus the NRG, and we're plotting the energy of the third excited state in terms as a function of how far of the cutoff. And you could imagine, well, you could say, well, suppose I just want to stop the numerical procedure here at this dimensionless cutoff energy, and then just stop the numerical procedure there, and then just compute the correction energy by using this formula, and you find that you typically, for large R, you underestimate the correction. So this is done at a fairly large R, an unnecessarily large R, to actually just to see that there's actually some flow in the energy. But if you're working this, if you take this large R and then actually just go ahead and compute this correction, you underestimate by like a factor of 10 the correction at this point. So yeah, so you can see it in the numerics that this type of perturbation theory does not work for large R. Now, where do we want to go? Are there any questions? Okay. Yes, so yeah, I'm just about to. Well, I'm about to elaborate on what to do with this counter term and show you how you can actually write down an RG equation and do some partial resummation. But even for large R, even this partial resummation doesn't quite do the trick. But I think that's to be expected, just because this is the relevant parameter that controls whether the perturbation theory is good or not. Okay. So let me just erase. So the expression I just erased was the energy correction coming from including all or attempting to include all the states in the high energy, from the high energy Hilbert space that were initially thrown away. Now you can imagine just keeping the states, just compute the energy correction coming from the states between one dimensionless cutoff and sort of increasing the dimensionless cutoff by 1. Yeah, it's a 1. So I'm going to get tired of. And so that all that amounts to is basically taking the expression that we had previously and taking the derivative with respect to this dimensionless cutoff. And yes. This? No. That's an R, sorry. Yes. And so what one can imagine, this is not the right sheet, is that instead of, as Slava was just alluding to, instead of thinking this is an energy correction, what one can do is to take into account the effects of the high energy Hilbert space. One can, or sorry, not the high energy Hilbert space, but just the wedge of states between energy cutoff NC and energy cutoff NC plus 1. One can imagine mimicking the effects of this energy correction. Let me just make sure. Yes, -2. By shifting the coupling constant in the original theory by this amount. So let me just be clear what I'm doing here. Let me call this lambda n plus 1, lambda. And so if I have a theory with coupling constant lambda n plus 1 and cutoff n, I mimic the effects of a theory with the original coupling lambda n, but with a cutoff n plus 1. And then you can write this shift in the coupling constant in terms in terms of a beta function. And what this beta function tells you is it tells you how one has to shift the coupling constant to take into account the effects of including states beyond your original cutoff. And the nice thing about this beta function is that you can then integrate it if you integrate this beta function you get that. Where I should be clear, this alpha is just some number. It's a constant that depends on the scaling dimensions of the fields. And so in particular, if I were to take my theory and simulate it, take my theory with cutoff n, dimensionless cutoff n, and simulate it with this lambda infinity, I effectively simulate a theory with coupling lambda n, but with infinite truncation, or no truncation. And so that's a useful thing, because that means you could take your theory and simulate it at some low cutoff. But if you just appropriately rescale your coupling, you can at least, to perturbative order, take into account the entire high energy Hilbert space. And so this expression for lambda infinity basically takes the second order contributions that you've gone through the trouble of computing and resums them. Okay. Are there any questions at this point? Well, yes, so that's what I mean by this. I want to use. Yes. That's right. But then, I mean, I went through this song and dance of restricting the delta E correction for states between NC and NC plus 1 So I could write down this beta function, which I could then integrate to take into account higher order corrections. I mean, I could have just stopped at when I wrote down that delta H and just said, okay, that's my correction to my lambda that I have to insert in the Hamiltonian that I want to simulate. But if I do this and then integrate things, then I include higher order contributions. If I actually if I went to third order and computed the delta E corrections, you get something that looks like disconnected terms that are basically related to the second order terms. So so if you want to resum all these terms to infinite order, this writing down this beta function is the way to do it. Would that do? Yeah, I'm not sure. I'm thinking not, but yes. So any other comments, questions? Then why don't we, so in the last hour that I have, I'll discuss how to use the truncated conformal spectrum approach to attack 2+1 dimensional systems. Yes?
Yesterday's discussion you said that when we do this calculation, there will be a four-dimensional point that shows that relevant operator does not reach the higher lower. Which one would that be?
Oh, well, I guess the crude way of seeing this is that, you know, when we were evaluating the delta E correction, we had this restricted sum, and the non-mixing of the high and low energy portions of the Hilbert space really amount to what the size of this matrix element is, or how this matrix element depends on the energy of this intermediate state. And the way you can see this is that, well, for example, here, if here's the correction to the coupling constant due to taking into account various states between n and n+1, and you see that there's a suppression factor of EC minus 2 plus delta p. And so delta p is the scaling dimension of the perturbation. If it's a very relevant perturbation, delta p is very small, and so that this correction term to the coupling is also very small. But if I had a marginal operator, delta p is 2. And so then the correction has no, the correction to the coupling constant or the correction to the energy has no suppression in the cutoff. And so that's basically where you would see it coming out of this calculation. So yeah, so this calculation depends on delta p being small. If it's 2, you can see that the correction terms that coming from high energy states are not falling off with the energy. And sort of, I guess one thing to note, I mean, you might think when you are evaluating this type of sum, you have to worry about two things. You have to worry about how this matrix element here is suppressed in energy, but then at any given energy or any given energy window, there's going to be some number of states. There's going to be a density of states at that energy. And so not only do you have to worry about what the typical matrix element is doing at that energy, you have to sum over all the states about that energy. And so one of the nice things that computing the 2-point function does for you is that it gives you information about how this matrix element is suppressed in energy, but it also includes the density of state contribution in a simple fashion. Okay, so yeah, let's take a break and then we'll come back and talk about 2+1 dimensional systems. So, in these last 15 minutes, I will discuss how one can use the truncated conformal spectrum approach, or just the truncated spectrum approach, plus matrix product states to give you information on 2+1 dimensional systems, but 2+1 dimensional systems of a very particular type. 2+1 dimensional systems that are conceived, represented as arrays of 1+1 dimensional systems, of coupled arrays. So you imagine the system at some array of 1+1 dimensional systems that are then coupled together through some perturbation, where if you number the chains I+1, and so forth, then the interchain coupling will take the form of, if this was Ising chains that you were coupling together through some spin-spin perturbation, it would be sigma I+1, for example. Now, the way we do this is through is to treat this system using DMRG. And so that means we have some matrix product state representation of this array of chains. And so maybe it would be, well, what I will begin with is to give you some insight onto, or as to when treating an array of coupled one-dimensional systems, when you would expect DMRG to work. I will tell you a little bit, or give you a super brief intro into matrix product states. So the way to do this would be to consider a general many-body state. So suppose you have some lattice system. You have some lattice system with n sites, and the dimension, the number of states on each site is d. Or we'll take it to be d. So that means if this was a spin system, then the spin would have d sites on any given site. So you would write if you had an n-site chain, you would write a general many-body wave function for such a state in terms of all the possible basis states. And the number, to do it in complete generality, the number of coefficients you would need would be the physical dimension of each site to the nth power. And so that's a lot of states. So this is not a particularly efficient representation for many body states. For particularly low-lying states in your spectrum. Low-lying states in your spectrum typically have many of these coefficients to be zero. So this sort of very general representation for the many-body state is inefficient. And so that's where matrix product states come in. Matrix product states are a much more efficient representation of low-energy eigenstates in a general many-body lattice system. And the parameterization one uses for a general MPS state has this form. The A's, so there are the A's are matrices. Which have size D, so they're D by D matrices. You have D of them, one for each possible value of the physical index. And so the number of coefficients, the number of parameters that this representation allows you is D times N D squared. So instead of having the number of coefficients explode exponentially in the system size, this representation only grows linearly. So in general, matrix product states are a much, much more efficient representation of any body state. But, of course, the question is, when can one use a matrix product state representation? Okay. Yeah, that's good. You're welcome. So the question is when can you use this much more efficient representation? And you can use it when the state you're trying to represent has low entanglement entropy. So specifically, if you have some pure state for the system psi, and you have your lattice system, and you divide it into two, you can always, using a Schmidt decomposition, you can always rewrite this pure state in terms of some basis of states, U and V, where U is restricted to subsystem 1, V is restricted to subsystem 2, and sort of the measure of how mixed up these two sectors are is given by the entanglement entropy, which is defined in terms of the coefficients of your Schmidt decomposition. So of course, if there was no entanglement between in the state psi, then the Schmidt decomposition would consist of just a single term, and that Ci would be 1, which would mean that the entanglement entropy was 0. Whereas if these coefficients are spread over a large number of the terms, then you get a much bigger entanglement entropy. And so the MPS states are good if this quantity is small. And And the way to understand this is that the maximum entanglement entropy encoded in an MPS state is basically related to the size of your matrices A. So this D here is your size of your A matrices, which is often referred to as your bond dimension. The bigger D is, the more entanglement entropy can be encoded in this state. And so the more entanglement entropy you can represent for a given many-body state. Now, what makes matrix product states so useful is that typically the low-lying states in your spectrum have small entanglement entropy. If you go mid-spectrum, if you look at some arbitrarily high-energy state, then your entanglement entropy is going to be very large, and MPS states can't be used. But for the ground state and the first few excited states, which is primarily what we're, well, at least for our purposes, what we're interested in, the entanglement entropy is small. And so let's consider this in a little bit more detail. Well, I'll give you, let me give you an example. I think that would be the, so suppose I wanted to compute the entanglement entropy for the ground state of a gapped 1D system. You can show sort of under rather generic considerations that the entanglement entropy is the log of the correlation length in the system over some lattice spacing. So that's what I mean by small. So regardless of the system size, the entanglement entropy for the ground state of a gap system is bounded. It doesn't, as I go to infinite system size, the entanglement entropy is controlled not by the system size, but by the correlation length. So if I want to represent this with an MPS state, all I have to do is choose D, my bond dimension, the size of my A matrices, to be on the order of my correlation length. And so that's always manageable. No, it doesn't, because the intent, of course, for a gap system, the MPS representation is very, very easy to come by. But even for the ground state of a critical system in 1D, we know how the entanglement entropy behaves. we know that it behaves as the central charge. It's controlled by the central charge of the critical system times the log of the length of the system. And so that means we would need our bond dimension for our MPS state to go as some power of the system size. But that's not so bad because, I mean, we can't go to infinite volume for a critical system, whereas we can basically simulate an infinite volume gapped 1D state or 1D ground state. But we can go because the needed bond dimension is only growing very slowly in system size for a critical system in 1D, we can still make progress. So doing DMRG for critical systems is more challenging, but not impossible. Is the what you want to take away from that sort of back of the envelope calculation. There should be a pat answer to this, but I'm not sure. At least I don't have it. That's a good question. If you have a lattice system, you have. I mean, it's not even so much ground states. If you have a lattice system, of course you have your states are not going to be just bounded below in energy, but bounded above, because the lattice system has a natural cutoff. And the states in the very high energy portion of the spectrum, right at the very top of the spectrum, are also low entanglement states. The states in the middle are the states that have usually volume law entanglement, so that their entanglement scales with system size. So badly for MPS representations. But for a lattice system, why the low energy and the very, very high energy have low entanglement intuitively? There are various But why? I mean, I guess the question, maybe a better way is yes, but I guess what I'm worried about is that I can go mid-spectrum, and while generically a state mid-spectrum will have volume law entanglement, there are states mid-spectrum that have small entanglement. Well, sure. I mean, but the question is you associate you're saying basically if I'm in a ground state, I have in a gapped ground state, I have exponentially decaying correlation, so I have small entanglement entropy. Yes, but the question is why are our decaying correlation necessarily corresponding to low energies? And I know that at least mid-spectrum there are high energy states that have decaying correlations. Yeah, no. So this, I mean, this you can prove. There are people, there are sort of people who are more mathematically inclined that have proven this, that there are bounds on the entanglement entropy for a gap ground state, but these proofs are not necessarily offer ready intuition. Yeah, so I'm more worried about these states mid-spectrum that have or ground state-like entanglement. Okay, but let's move on. So this is the entanglement entropy for 2D systems, for one-dimensional systems. But what happens when you look at the entanglement for a 2D system? If I have a 2D system and I partition the system into two, the entanglement and the length of this boundary is R. Then my entanglement entropy is going as the length of the boundary. And that's unfortunate because that means the bond dimension I'm going to need is going to be exponentially large in the boundary, the length of the boundary. So generically, DMRG and MPS is hard, and using MPS states in 2 dimensions are hard, is hard. And so that's why you have all this work on generalizations of DMRG to higher dimensional spaces, which usually go under the name tensor networks. Although, yes? This is actually for gap systems. If you have gapless 2D systems, then, well, actually not a lot is known, but you would expect to get terms. You would expect to see area law terms and then area law terms with logarithmic corrections. Or maybe not even, maybe logarithmic corrections in sort of the transverse direction to the cut. So yeah, so for gapless 2D it gets worse, but even for gap systems in 2D, the entanglement entropy is huge, because even in a gap system, the entanglement across the cut is going to be bounded to within a correlation length, but since you're cutting along some length of the boundary, the entanglement entropy will necessarily scale the length of that boundary. So MPS states in 2 dimensions is hard, and so the question is it's hard because of the area law, and so basically the question becomes, so to speak, is how to bend the area law. And that's where the truncated conformal spectrum approach comes in. So as I say, what we do in 2D is treat the 2D system as some one-dimensional array of coupled chains. Where each chain is of length r, and that, you know, well, the example I will consider are coupled quantumizing chains, and so the interaction between the chains we're going to take as some spin coupling. So this would be the ith chain, and this would be the ith plus 1. And we treat the chains in a 1D DMRG algorithm. In a 1D DMRG algorithm that treats each of the chains like it's some large spin. So each chain is like so each chain is one lattice site in the 1D DMRG, and instead of if you had a treating 1D Heisenberg spin chain in a 1D DMRG, the physical dimension of your site would be 2. But here, the physical dimension of each site is, well, before truncation is infinite. Now, nonetheless, our MPS representation of this coupled chain system is still going to have areal entanglement. But the way we keep the entanglement under control is we keep the length of the chain small. And, well, okay, you can say, well, isn't that going to be problematic? Now, the answer is, at least for many questions, the answer is no, because we know that finite size corrections are exponentially small. So if delta is the gap in the full system, in the 2+1 dimensional system, our finite size corrections are going to be suppressed by delta r, or e to the minus delta r, exponential delta r, for exactly the same reasons that I discussed for the one-dimensional TCSA. So a key element of this is that we're representing the chains as a continuum system. If we were to represent it as a lattice, then we would not necessarily get finite size corrections that were exponentially suppressed. But because we're working with a continuum field theory, our finite system size corrections are small. And so we don't have to make the chains very long to be in the infinite volume limit. And if we don't have to, if we can keep R small but still be in the infinite volume limit, it means that we can keep our entanglement entropy under control, which means that we can find efficient or MPS representations with rather small bond dimension, and have these MPS representations accurately describe our 2+1 dimensional system. So for the specific implementation, so for the implementation of our quantumizing chains, our coupled quantumizing chains, we keep R small. Now, of course, the other thing we have to do is, if we're going to treat this array of chains using a one-dimensional DMRG algorithm, we have to make the physical dimension of each site finite. So we have to truncate the system. We have to truncate the Hilbert space of the 1D chain. And typically, we can get away by keeping order 100 states on each chain. So that would be the physical dimension of our MPS representation. Would be on the order of 100. It can be up to 500, but typically it's order of 100. Now, just like the TCSA, this is actually an okay thing to do because basically we are taking our chains and perturbing the chains by a spin-spin coupling between the chains. So phi I plus 1 is our perturbing operator, and the scaling dimension of this is still relatively small. It's 1/4. So the truncation is not an unreasonable thing to do for this system. Okay. So in the last 12 minutes, I will just run through a number of checks that treating coupled Ising chains like this is not such a bad thing to do. And so the first thing you might want to check for is that I write down my MPS representations for these coupled chains. So I have my coupled chains. I then do, I have my MPS representation for my coupled chains, and then I compute the entanglement entropy along a cut between two of the chains. And if my chains are of length r, the entanglement entropy I should compute should scale as r. Now, it's a very elementary check, but it's something you should do to see if you're getting some sensible results. Because remember, r is only, when you represent the chains in the MPS representation, the r is just buried in matrix elements. It's not obvious that the r is, it's just like, it just sort of amounts to a rescaling of your coupling constant. So it's not clear once you actually get your MPS representation and go ahead and try to compute the entanglement entropy, whether you're going to get something that scales as r. But you do. It's not going to let me down. So this is a plot that computes the entanglement entropy as a function of r, and you see it's a straight line. It's in the gapped phase of the coupled chain system, and so you have no problems reproducing the area law from this type of calculation. So at least, barring anything else, you're not doing something ridiculous. One thing I should note is that, which I haven't said, you might ask, how large are these arrays? How many chains do you have in these arrays? So one of the nice things about MPS technology is that there are various infinite volume algorithms. So you can actually write down MPS representations that have an infinite number of chains. So you can have anywhere from 2 to infinity. So at least in one direction of your two-dimensional system, you can go to infinite volume. Not in the other direction, but at least in one direction. Now, a second non-trivial check is that if you look at the ground state energy of this coupled chain system, it has to, well, you have to have a term that scales, that basically marks the vacuum energy density, and so scales with the volume of the system, which is the number of chains times r times some scale. And then actually you can just apply, I mean, there's two ways of viewing this coupled chain system. You can view it as some 2+1 dimensional system, or you can view it as some weird one-dimensional system with many degrees of freedom that are coupled in a very peculiar way. And so that means you can just take what you know from one-dimensional field theories and you know what the form of the ground state energy is, which it has this, the vacuum energy density, and then well, here, no. It has a correction due to virtual it has a correction that's exponentially suppressed in chain length. It has a correction that comes from virtual excitations of the lowest lying excitation in the system. So this is an integral over the momentum of that lowest lying excitation. This is the energy of the lowest lying excitation. So and then that's the chain length. And so that's exactly what you expect the energy of the ground state. So you can actually you can do a consistency check. You can use the DMRG to measure the gap in the system, the excitation gap in the system, and then you just plug it into this formula to see if you reproduce the ground state energy. And if everything is working, that's what should happen. And so that's exactly what you see. You see so this yellow line here is the infinite volume term, and then you have, here in this inset, you have this exponentially suppressed correction of the coming to the bulk vacuum energy, and this blue line is this correction as computed analytically. So everything is consistent. You would expect things to be consistent here because you see that because this exponential correction is exponentially small as you make the chains longer, and you know that for small chain length, and here the chain length is very small, you know for small chain length that your entanglement entropy is very small, and so the MPS representation of the coupled chain system is going to be very good. So it's not surprising that things are working here because that's precisely where you would have the best shot at things working. Yes? No. So you would fix the number. I mean, in this numerical calculation, you fix the number of sites per chain, the number of states per chain, the number of states per site, and you just vary R. Because you remember, I mean, this is just quantumizing. So I gave you the Hilbert space of quantumizing in the first lecture as a function of I mean, everything I wrote down, the energies, the matrix elements, was for arbitrary R. And so I say, okay, I'm going to truncate my Hilbert space at some fixed number of states. So I keep the vacuum states in both sectors. I keep, say, the single particle states up to a certain momenta, or a certain integer quantization of momentum. I keep the first particle states up to a certain momenta. I keep the two particle states up to a certain momenta. So I have the same number of states per chain, per site, but their energies, of course, and their matrix elements depend on R, but in an analytic fashion, which I know ahead of time. So there's no issues in incorporating that into the DMRG algorithm. So the final I go back a slide. So suppose here. So the phase diagram of the chains, suppose I start out with the chains in the disordered phase. Remember, I described the Hilbert space for each chain. It had its Hilbert space had a different description in the ordered phase. All the Neville-Schwartz and the Ramon fermions had to come in pairs in the ordered phase. In the disordered phase, the Ramond fermions came in odd numbers, and the Neville-Schwarz fermions came in even numbers. So imagine I start the calculation, the uncoupled chains in their disordered phase with some gap, which probably I shouldn't use delta. So let's call that M1 chain. The mass of the Majorana fermions in a single chain. And then I turn on an interchain coupling. At some critical J, interchain coupling, I'm going to go through an ordering transition. So for understand this. Yeah, see, because it's 1 over. So at some critical J, I'm going to undergo an ordering transition. And that ordering transition is going to be that of 2 plus 1 quantumizing or (3D) classicalizing. So the ordering transition is something that we understand. We know the critical points. We know the critical exponents to, well, now because of Slava, we know the critical exponents to ridiculous accuracy. And so, but the question is can we capture this critical point with our DMRG algorithm in any fashion? And you wouldn't necessarily expect to be able to do so because, as I said, in general, critical points, even in one-dimensional, are harder for MPS representations, but that's doubly true in two-dimensional systems, never mind, two-dimensional critical systems. But because we have a relevant perturbation, and because we can keep the chain length reasonably small, we can, here we go. We can make a reasonable estimate of the critical exponent. Again, nowhere nearly, when this work was done, it was not anywhere near the same accuracy of the critical exponents as Monte Carlo could do, and it's certainly nowhere near as accurate as conformal bootstrap, but you're within a few percent. So for this particular example, DMRG produces the critical exponents within a few percent, which is pretty good considering the method. So it seems, so what I want you to take away from this is that the method is at least working in one example of a 2 plus 1 dimensional system. Now, I don't have time, but the final thing I'll say is that one of the nice things about using MPS representations for these studying for these 2 plus 1 dimensional systems is that one can sort of borrow off the shelf other improvements in MPS technology, and in particular you can study time-dependent behavior. You can study time-dependent behavior using ITEBD, or just TEBD, which stands for time evolving block decimation, which is a MPS approach to study real-time evolution in in 1+1 dimensional systems, but now we can adapt it to study our coupled arrays of chains. You can also borrow approaches to study finite temperature correlation functions, and so on. So it means that this particular way of representing 2+1 dimensional systems gives you a lot of tools for which you can study them. So that's it. Okay. Yes. Yes. Yes, yes, you do. This work by Charlie Kane and company. And now many people, yes. Mm-hmm. Yes, so, I mean, the other system that we've studied are coupled Luttinger liquids. And so, I mean, with Charlie Kane's coupled, are using chiral Luttinger, he uses chiral Luttinger liquids to represent his quantum Hall states. And so I mean, that's even easier for us because the space of a chiral Luttinger liquid is the square, in terms of size, is the square root of a full Luttinger liquid, because you only have one chiral sector. But we've only studied non-chiral Luttinger liquids, and then our motivation was more studying coupled one-dimensional Bose gases. But yeah, no, certainly that would be a problem that this could attack. Well, you do need, I mean, if I mean, we were taking advantage of the fact that we were representing each chain as a field theory. You don't need to, really, all you need is a model that's integrable. Because all you really, I mean, what you need is you need to be able to compute the matrix elements between some operator that some coupling between the chains. You need to be able to compute the matrix elements of that operator. And so all you really need is integrability. You don't need to use a field theory representation. But so you could look at, for example, you could look at coupled Heisenberg chains. Because Heisenberg chains are integrable, and so you know, and plus the matrix elements are known. But for the field theories, I mean, all we needed was that, for the Ising field theories, all we needed was that this chain length was, I mean, we want, well, actually, ideally what we want is that the chain length times the mass on the chain is much greater than 1. And what we discovered numerically was that even if the two-dimensional gap, so that not the gap on the individual one, not the gap on the initial uncoupled chains, but what we discovered was that even if the gap in the full 2D system was order 1, we got reasonable results. And how do we know that? Because we were able to reproduce critical exponents within a few percent. So it would suggest that there's a certain, that even though this is the condition that we need, we can get away with something like this. Although whether this is one system, and you could argue that quantumizing is rather forgiving. And maybe for more general systems, we will have less luck, but that's something to be seen. I mean, our one of the things we are working on currently is coupled Heisenberg chains, so no field theory, and because we can use one might think that one could not get to very long chains in such a system. If you just there have been some calculations of entanglement entropy in 2D Heisenberg. So you can ask, well, how much entanglement does 2D Heisenberg have? And it looks to be like maybe you could get to, you could look at states with, or chain lengths of 2D Heisenberg, you could look at composing a 2D Heisenberg model out of chains that have up to 20 sites, and the numeric should work. But what would be nice about that, if that's actually true, is that because you can have their various infinite volume algorithms, you could study a 2D Heisenberg that's infinite in one extent and maybe has 20 sites in the other direction, which would be competitive, I think, with the best 2D DMRG attempts to study Heisenberg models. Sort of what we'd be interested in comparing to, so one answer is yes, that would be nice, but people do 2D DMRG on sort of using other approaches, and they can't get to very big systems. And so the point would be to really just do better than what other people are doing, rather than being in a system, being able to get rid of all finite system size effects.